Hi everyone, I'm very excited to be here. I just joined DTU recently. I joined in October this year. And this day is very special for me because it will be my first public presentation here at DTU, and especially it's being recorded. So it's a very special day for me. And because I just joined the university, I decided to take a few slides to present myself, show you a bit of my background, and then I will proceed with a bit of my research vision and why I joined this university and what I'm thinking about. And then we'll go a bit on some approach that I plan to present to you, and that's optimization under uncertainty. But basically, I am an assistant professor at the EMA section with Jalal and Licio. And I did a PhD in Oxford, and then 2 postdocs, one in Oxford, and a short postdoc in Stanford before joining DTU. And I have a background in control theory. And I've been working a lot with stochastic optimizations, and just a brief of summary so that you can have a look. And why I'm doing research, and I'm interested in decision-making under uncertainty when the consequences of taking the wrong actions can be catastrophic. And this can be seen in general many applications that you could imagine that could happen, like space explorations, or maybe a robot that's operating in a patient and somehow takes a wrong action and the patient dies, and what we'll do, who is to blame? And I'm interested in these problems because they have a complexity and decentralized decision-making nature. They have sources of uncertainty that somehow we think of them as representation of reality, right? So this is something that we wish the reality will be it, but we don't know, so we presented it, and we call this label uncertainty. And most importantly, what I'm looking after in my vision, in my research, is to provide certificates, right? So I want not only to design something that I can operate, which sometimes is fair, is the only thing you could do, but I'm also very interested in attaching certificates. So I want you to make an action, but within some probabilistic model, I can guarantee that your action will behave well with certain probability. And that's the philosophy of this talk. And the main application that I will work is that of power system, because it has all the features that I presented in the previous slide. And as you can see, for instance, I'm just saying you have several markets in Europe, and like it's a cascade feedback mechanism where the decision of one market will impact the decision of another market, and you have uncertainty everywhere. We have this hierarchy of feedback control. That's the way I'm looking at it. And somehow you need to make sure things behave well. I have a very pictorial abstraction of what I just described. It is idea where you have somehow a dynamics, a model that you don't know, is sort of a black box. You get data, and you make decision using that data, but somehow your decision feed is back, right? So alter future states of this black box that I'm calling dynamics. Well, over the years, I've been mapping many areas, many tools that somehow try to address this problem. It's a very hard problem even to frame, but what I'm planning to do in my research is to combine different tools like optimization, control, stochastic calculus, and formal methods. So these are techniques that span mathematics, computer science, engineering, and operational research, I'll put it this way. And, well, it's interesting because I recently became a father, and then somehow you start trying to connect your sort of daily life with your research. And I've noticed that I every day facing a very difficult decision-making problem. That is when my daughter is crying, I don't know the reason for it. So I need to decide on a bunch of actions, right? I need to decide whether to change the diaper, put her on a stroller or in a wrap, take for a walk. I don't know how much time I should take. So there are all these discrete actions that I have to take because I don't know why my baby's crying. So it's a daunting decision-making process. And I was very sad too because despite having able to work out this analogy, I fail miserably on this task every time I try to solve it. So, but that's it. I mean, what you can do, you have hope, right? So hope. So I always try to do research, but here is a problem where, because I mean, if you look at my sort of the problem I described, right? I want to get a guarantee. What's the probability that I do certain actions with my daughter and then she stops crying? That's my goal. And I want that to be ensured that I'm making the right decision. Well, here is a problem that is related to this problem that I think, at least I wanted to convince you that we have some ways to somehow solve this problem. And the problem I'm interested in is called optimization, is called chance-constrained optimization. You have an objective function, and I'm calling it, without loss of generality, I'm considering my function to be linear, but if my function is not linear, writing its epigraph reformulation, you can always consider the objective function to be linear. And the problem, the meta problem I'm thinking about it, rather than optimizing, finding the optimal solution for that function subject to some constraints, I allow some level of constraint violation, right? And I want amongst all the points that satisfy my constraints with high probability, I want the points that minimizes my objective function. So you see, it's a bit different than a regular optimization problem. It's very hard, that you can imagine. If you think about it, there is this P that you could think of probability-based function. I may call it probability measure. But there is this metaphysical-like assumption that I'm saying. There is this probability. I want to solve that problem under those constraints. And I have data, right? So you have a bunch of samples, and let's say realizations, as you can think of it, I will denote throughout this presentation as capital S. So omega 1 up to omega m is the bunch of samples that I collected. And I'll be using a bit of maybe different notations than what you might use to. But I would like you to focus on the main idea. I mean, there'll be some equations, but let's say I don't want to lose you because of equation. I just want to give you an overview of what we can do when studying this kind of problems, and you have IID data points from this probability measure. And I want to recognize, like you always stand in the shoulders of giants, right? So the main results in this theory has been developed by a group of Italian research of northern Italy, and then so I just wanted to recognize them. This was not developed by me, but they were thinking, well, what's the most natural way you could do? If you formulate this problem, and you have a finite number of realization, I think, and I would agree, the most, so just so that I don't sort of establish a notation, X star of S is the optimal solution of the problem where you replace the probabilistic constraint that was in the previous slide. Trying to go back, but yeah. So I'm replacing the probabilistic constraints with enforcing constraints at each realization. So for each omega in this discrete set, I enforce the constraint that I have, and I call, this is a normal optimization problem. You can sort of code it, and I'm calling X star of S, because this optimal solution is now a random variable, and it's a random variable defined on this space P to the M, I'm calling it. And then I want to say, well, if I solve that optimization problem, I'm interested in the following property. What's the probability that a new sample comes and I violate the constraints? So this is a simple question. And the cornerstone, one of the main results of so aqui, let me just go back a bit and say, think if this is an instance of that optimization problem there. So you are minimizing x2 is a two-dimensional optimization problem, and each of those lines is one of these constraints, right? So you have the g of x and eta for a fixed omega is one of those constraints. In that case, you have 6 constraints. And you are minimizing x2. So you are solving an instance of this toy optimization problem that I've been showing you, right? And then there was this powerful result. And it's very, I'm saying this may be hard to pass in the first time, but it's basically saying if you solve that problem, which I will call the scenario program, with constraints only enforced in the available data set, the probability that you violate constraints being larger than epsilon is less than or equal to that quantity, that tail of a binomial distribution. So that's what this is basically saying. It's important that this result is sort of universal. It holds true as long as the function g is convex. It needs to be only convex on x. So as long as you are solving a convex optimization problem, once you fix your realization, then this result's true. And more importantly, there are a class of these problems for which this bound holds with equality. And these are the class of problems for which, with probability 1, I'm solving a two-dimensional optimization problem. So there is always 2 constraints that is supporting my optimal solution. In this case, they coincide with active constraints. I don't want to, what I'm saying, I will call active constraints, but this is not exactly true in the theory. It's called support constraints, which are the constraints that, if you think about it, if I removed any one of those green constraints that are supporting my active solution, the optimal solution would change. So if I remove the constraint on the left, the optimal solution will change. And if this number of these important constraints coincide with the dimension of the optimization problem you are solving, then you can exactly characterize the violation probability of my solution. And like going back to the analogy, so if this would be true to my daughter's problem, I could sort of ensure that my set of actions, I could quantify how many attempts I should do to guarantee a given probabilistic certificate. So this is clear, the message, right? So you start with a chance constraint, you get sample, you solve an optimization problem, and then you attach to this optimal solution a probability that you violate the constraints for a new realization, right? So let's keep this in mind. I think that apart from any notation that you can see, that's what I would like you to take from this slide. And then, okay, you see, okay, this is very powerful, it's universal. But it would be nice to think about what are the limitations, right? Can you think of any limitation on what I just described? Anything that bothers you? Anyone wants to say something? Yes?
Very quickly with the number of scenarios.
Sorry?
The bound scales very quickly with the number of scenarios.
Yes. Yes, so you may not have enough data points. May I rephrase this? Yeah.
Or if you have too many scenarios, then the bound is like very large, I guess.
Or my optimal value could be conservative too, right? Because I'm enforcing that many constraints. I, first of all, may not be able to solve this optimization problem because I'm solving with too many constraints. And then, as a result, my optimal function, my optimal performance will be conservative. Yeah? Shall we?
But what about tails?
That's right.
But what about you were talking about catastrophic failure, so what about the tail of the distribution, which you might not achieve in sampling?
Yeah, so you say the epsilon is too small, right? For instance, you could see, I haven't done this, I should have put it here, but the equation, the sample complexity scales with 1 over epsilon. So say if you are interested in a 10 to the minus 9 event, then you need 10 to the 9 samples to ensure the guarantees I'm saying. So is that what you were referring to, Shubi? Yes, that's a limitation, yes, I agree. And another limitation that you could think of it is that this probability distribution, what if this probability changes over time? So I get data, but then when I'm when I'm applying this sort of optimal solution, the P is not the same, right? Could also be, those are very good points. And how about if this problem is non-convex, right? Could you apply this theory for a non-convex optimization problem? And I mean, this is a very nice question, but I just wanted to convince you that the same problem, right? The whole theory relies on the fact that there are few constraints supporting the optimal solution. So think about you have a non-convex problem that you are trying to minimize. I don't know, I don't know if I'll make this right, but sort of you are trying to your optimal objectives, minimizing x2, and those are your constraints. So your physical set is all those regions inside here, right? Yes, right? I meant you are trying to maximize. Say you are trying to maximize this function. So the optimal objective will be somehow there. I'm not drawing these exactly, but you can play any of those constraints, if removed, will lead to the optimal solution to change. So you could have as many support constraints as the dimension of the problem you're trying to solve. And that's like an issue. So in the convex setting, there are a bunch of theorems that in convex analysis called Helly's theorem. And that's what's behind what I just showed you. You could upper bound the number of support constraints if all those constraints were convex. Okay? We can discuss these, but I think that was more or less what I'd like you to get. It's a very powerful tool, works well for convex problems, but there has been extensions, right? So I'm asking this question, but at least for the non-convex setting, I will mention some papers that have tried to deal with this case. Sure. But now I wanted to address one of the drawbacks that you mentioned is, okay, I may not be able to solve the convex optimization problem if I have silent Romao. I'm not gonna, this is a limitation that I recognize of this approach. But you may make a decision, but you want to sort of improve your decision by removing constraints. Because if I remove some of the constraints that I had before, right? If I removed it, the feasible set of the resulting optimization problem will be larger, and I will improve my cost. So there was advancements in the theory that sort of say there are bounds, much like in the spirit that I was presenting to you, when you allow constraints to be removed. And those bounds, they look like the one I'm showing. Well, I don't want you to get bogged down at this stage on this exact expression, but one thing that bothers me a lot was that combinatorial factor there, while in the previous case, I sort of hinted that the bound was tight, I was sort of wondering, why do we need this combinatorial factor? And that was sort of the question that I was asking. And because, well, that would be nice, because I mean, this whole approach is that as more constraints are removed, the more constraints are removed, the cost will decrease, and I sort of can quantify the risk. That's what this graph is saying. The red line is the cost, and when the samples are removed, and the blue line is the risk that is increasing, right? So you sort of improve your cost, but you pay a price in terms of risk of your solution. And then, so when I asked myself that question, somehow I went through this simplest problem that I could think of, which is that of getting, suppose that this distribution P is uniform in the interval 0, 1. You sort of have some samples, and you want to minimize what's the maximum sample, right? So that's what you want to do. You want the optimal solution of this problem is basically the largest sample between the samples you have so far. And you want to say, once I get that solution, what's the probability that I collect another sample, and the sample is on the right of the largest samples that I've collected so far? That's the problem I was sort of playing with. Well, this is a well-known problem in statistics. It's called order statistic. But I went around and said, what if I remove? So I sort of, you wander around, what's the violation probability associated with this problem? And then after some time and after some calculations, right, I'm saying this V of S is the violation, which is the probability of being to the right side of the largest sample that I've collected so far, right? And then you can sort of play, and what if I remove samples? How that number sort of evolve? And after a few sort of manipulations, you can sort of see analytically that violation probability is equal to that equality in the green box, on the right side of the green box, which somehow differ, right? So if you compare those two, you can see that there is a gap, especially when R is equal. When I is equal to 0, you recover to the previous result. When R is different from 0, R namely the number of samples that I'm removing, then those two bounds, they do not coincide. And that bothers me. So that was sort of one realization. And then, okay, maybe, what if I solve a slightly more complex problem, right? It's the same, similar flavor, but now you think about uniform distribution, you get samples, but now you're trying to minimize the minimal width interval that contains all these samples. Now it's a two-dimensional optimization problem that I'm solving, rather than a one-dimensional one. And I did the same trick. So I sort of say you could relate the violation probability is 1 minus the length of the interval in the end. And now the computation is slightly more complex, but you could play a bit. You could split the probability violation into two complementary events. Each of these, this probability can be computed analytically, and that's what I'm showing all the steps, and these are here just for reference, but what I'm saying is that you could then compute analytically the violation probability for this two-dimensional optimization problem. And then you will notice, and here is this result. So here is the result for the two-dimensional optimization problem, and you see they differ. So I solved two very toy examples, and they compared the violation probability. I could see there was a gap there in the literature. And there was, I'm going back a bit, so it was a joint work with both of my PhD supervisors at the time, in Oxford, Costas Margelos and Antonis Papachristou. And we sort of, the starting point was this notion of compression set. So basically, what we knew is that there is such a thing as a compression set, which is basically the important, I'm sort of oversimplifying. If you go to the literature, it's more technical than this information, but I don't want to go into that. But basically, you could think of compression set are the samples that leads to the same optimal solution, had you enforce all the constraints at once or only the samples in the compression set. And if this compression set is unique, so there is existence of a compression set and then uniqueness, then it was known at that time in the literature that the bound holds with equality, and then the C is the cardinality of this unique compression set. And you could see that I would recover the two analytical bounds had I applied this theorem to both of those problems, because I could show there is only one compression set in the first problem, and there is only two samples that forms the compression set. And if I remove samples, then I would add samples to this compression set. I just need to count. And then the idea, the starting point, and is in this result is in this paper, but could we then show, so from the description I show you, could we then show that there exists a unique compression set for what I'm calling sampling and discarding scheme? And that was sort of how this research started. And we ended up finding a positive and a negative answer to this question. A positive one is that, yes, there is a way to remove samples for which you can prove the existence of a unique compression set. And this way to remove samples, because the previous bound, the one that had that combinatorial factor that was sort of bothering me, that bound is more general because it holds for a larger class of removal, way of removing constraints. Now I'm fixing a single method to remove constraints. And this method would then, for this method, we could then prove the existence of the unique compression set and improve and get rid of the combinatorial bound that was existing in the literature. And the removal algorithm is, for me, very natural, is that you get all the samples and you solve a cascade of optimization problem. And I'm assuming that I'm removing, I mean, this is just to give you an idea. I'm jumping a few sort of the details, but if you are interested, we can discuss it more. But I'm removing basically the active constraints at each time. For instance, I solved that optimization problem and I recognized that those were the two active constraints. And then I removed those active constraints and solved yet again another optimization problem and remove now the blue constraints. And I could, if I proceed in doing so, I could offer that guarantees for the optimal solution. And those guarantees, that guarantee holds true without the combinatorial factor. So basically for this specific removal scheme, you could better characterize the violation probability compared to existing approach in the literature. So that was sort of the main contribution of this line of work. And we also show that as much as in the case where you don't remove constraints, there is a class of problems for which the bound without the combinatorial factor for this specific removal scheme holds with equality. So somehow you sort of extend the results where you don't remove constraints to the case where you could remove constraints, and you do so with a better bound. And why? What's the consequences of this? The consequences of this is that you can better characterize the violation probability, so you somehow, for the same level of violation, you could have removed more constraints. And that could lead to a much better cost improvement. This is not a general statement because it depends on the geometry of the problem, but that's sort of a very practical consequences of what the result I just described. I think I just make some remarks, and this is more technical, but in doing so, we do so without relying on a critical assumption of the previous result that requires all the constraints that you remove should be violated by the final solution. So our result does not need that assumption, but this is slightly more technical. I don't want to get into that, but I just mentioning that you can then, for the same level for a problem, I'm just illustrated here that this was a linear program, very simple, but you could grow the dimension, and for the same violation probability, you could improve the cost by this factor that appear in the table. Yes, I think that's the method I would like to present to you. This was just one thing that I thought connects well with the type of problems we are dealing with. And here I listed some developments of the theory, sort of more recent developments, including there was a very interesting development that goes under the name of weight and judge, that sort of your guarantees will depend on the number of active constraints. Here you could a priori sort of have a dispack bound on the violation probability. But if you wait to solve the problem, you don't know. You solve an optimization problem, you wait until you see the number of active constraints once you solve the problem, and then you assert a certificate that will depend on that number. roughly speaking. So this was an interesting development, and many others. And recently, I've been interested in investigating this theory to do uncertain quantification, it's called. And there is a very well-known statistical approach called conformal prediction, and I've been interested in sort of bridging the gap between these two words. And we have some preliminary results, and if you want to discuss more, I'm happy to. But I think that's all. That was my message. It was a bit of down to, but I would like you to reflect on sort of the usefulness of this approach. I'm not saying that this will solve all your problems, but that's more or less the philosophy in which I'm approaching this decision-making and uncertainty. I want something that I can not only solve or is very computation intensive, but I can sort of attach this kind of certificate to the optimal solution. And at the very worst, if you didn't like the approach or if you haven't found a very concrete application to the problems you were thinking, I would like to remind you this quote that says, for a man with a hammer, every problem looks like a nail. So at least you have another tool to think about it. And if you, when you was in the future career, if you think about something that resembles this, then you have another set of tools to try to approach this problem. And also reflect, and that's more, if I may, an advice for all of you, is that when dealing with uncertainty, it's very hard. There are many different interpretations of what probability means. If you go and search for objective probability, subjective probability, it's very sort of live in the field of economics. So it's not a very complex problem, but in this case, what helped me was find an analogy with a toy example, work it out, and if you do it well, if you exercise, if you manage, sometimes, if you manage to do the right abstraction, then you find the answer to the problem you are looking for. And because otherwise, you get into this other quote that I find it very interesting when dealing with this problem, is that we are always implicitly relying on the following. We are always relying that the future's past resembles the future's present. And that might not always be the case. And just to reflect, I think that sort of was what I would like you to get from this talk. And thank you very much. I'm happy, I'm open for questions.
Understand all the what you explained because it's not my area, but I wanted to be sure, are you always assuming that this uncertainty, the objective functions, would always be linear with this minimization equation you have? No,
I think that was, I hinted a bit, it was very fast at the beginning, but think a bit, if you have so if you're saying, think if you have a problem that has, the function is convex, and then you have the same constraint that I had before, right? I don't want to write with what is inside. But then you could write its epigraphical reformulation, right? So you could write this problem is equivalent of a problem of you minimize t subject to the probabilistic constraints, right? And then you do f of x less than t. So this will minimize over x and t, this will minimize over x. So increase one variable, but now my objective function is linear. And I could have deterministic constraints in this original formulation. That's why I'm considering, just for the sake of presenting the problem, and I don't want to, it will be easier mathematically rather than writing functions. But that's not, is without loss of generality if you pay the price of increasing one optimization variable. Wait.
Any more questions? So, may I ask a question, please?
Yes.
So you're trying also to find the number of samples we need to draw to represent the uncertainty, right? And then how many constraints we need to have for each sample. But instead of playing with number of samples, can also play with how we sample, how we do sampling? Is there any way we can do that? Instead of random sampling, we go, I don't know, for importance sampling or any other technique?
Yeah, I mean, so you could see on your framework, the framework you are presenting, right? So say you have a prediction, and your prediction has some probability attached to it because you've done so. So you not only have a point, but and then you want to solve an optimization problem to make your final decision. Well, that distribution may be hard to sample from, right? And then you may need to use numerical algorithm to get samples from that distribution. And there'll be errors, right? And so the issue is that these guarantees are given with respect to the probability over which you are sampling, which may not coincide. So there is this a bit of gap there. But
We don't know which area we have to sample X ante. If I understood correctly.
yeah, even if this P is so high dimensional, even sampling, obtaining the capital S set might be a hard problem. So I'm a sort of getting, for my point, I get those sets as given.
Any last question? Dick?
You don't have any probabilities attached to your event space. Is there a reason for that?
Here you mean in this problem? I think I have it here. I got rid, for instance, that expression there, right? So there is this calligraphic P. I'm considering all the samples are sampled from this probability space, right? Is the measure space that I'm calling omega, with some collection of sigma algebra and P.
Now, have you thought about how to turn that model into a market model?
I'm trying to think about it. Yeah, that's
May I ask my last question? Also, can you say also, if we have a chance to have analytical solution for chance constraint, do you recommend that, or?
yeah. The result I've shown you, I don't know, was it the question? Because there are no results developed by Nemirovsky and others, where there's results, they don't assume anything about the P, right? But if the P is log concave, right, the density associated with the probability measure P is log concave, then you could somehow, and in some cases, even reformulate it as turn that just constraint into an SDP sometimes and solve it exactly. But you pay the price that you are assuming something about the P.
And the benefit is that we don't need samples.
Yes. I mean, you need the statistical properties of your density, covariance, median, but no samples in play.
Good. So if there is no further questions, so maybe we can conclude the session. Thank you, Licio.
Thank you.